Hello everyone. I am Shivasankar Hasda. Welcome back to my YouTube channel, your KGPN Bro. In today's video, I am going to discuss about a very interesting topic of coordination compound, which is nothing but the VBT. So let's start. VBT. VBT stands for valence bond theory, and this theory is developed by Linus Pauling. So let's see what are the main features of this theory. So here is the main features. Point number 1. Metal ion forms coordinate bond with the ligands while forming complex compound. So whenever a metal ion forms complex compound with its ligands, it forms coordinate bond with the ligand. During the formation of coordinate bond, a metal ion acts as electron pair acceptor. Now, in order to accept electron pair, metal ion provides vacant orbital, and the number of vacant orbital provided by the central metal ion is equal to the coordination number, and which is equal to the number of lone pair to be accepted. So these vacant orbitals undergo hybridization or intermixing to form vacant orbital before forming the coordinate bond. So finally, these vacant hybrid orbitals of central metal ion forms coordinate bond with the orbitals of ligand containing lone pair. So this is the overview of valence bond theory. That means during the formation of complex compound, metal ion forms coordinate bond, and during the formation of coordinate bond, metal ion act as electron pair acceptor, and in order to accept the electron pair, the metal ion provides some vacant orbitals, and the number of vacant orbital provided by the central metal ion is equal to the its coordination number, and these vacant orbitals undergo hybridization or intermixing in order to form vacant hybrid orbitals, and these vacant hybrid orbitals finally forms coordinate bond with the orbitals of ligand containing lone pair. So let's see what do we mean by a ligand and its types. So ligand is nothing but chemical species containing lone pair which forms coordinate bond with central metal atom by donating its lone pair. So it's basically nothing but a chemical species containing lone pair and which forms coordinate bond with the central metal atom by donating its lone pair. So it's basically act as an electron pair donor, that means Lewis base. And it is two type. One is the strong field ligand and another one is weak field ligand, that is SFL, and one is WFL. So strong field ligand, they are capable of pairing of the unpaired electron present in n-1 d orbital of central metal ion. They can pair up the unpaired electrons which are present in n-1 d orbital of central metal ion. If n-1 d orbitals are involved in hybridization, then the complex formed will be known as inner orbital complex, and this SFL, that means strong field ligand, generally prefers inner orbital complex. And generally carbon and nitrogen donor ligands are act as strong field ligand, that means carbon monoxide, CN minus, NH3, EN, NO2. These are basically strong field ligands. And one point to be noted is that with 4D and 5D series element of the periodic table, all ligands are strong field ligand. Here is the weak field ligand, that means WFL. In case of WFL, no pairing of unpaired electrons present in the n-1 d orbitals of central metal M. No pairing takes place. If only n orbitals, that means only outermost orbitals are involved in hybridization, then the complex formed will be known as outer orbital complex. Example of outer orbital complex is sp3, sp3d, and sp3d2, etc. Here it should be. WFL generally prefers outer orbital complex, and it is basically the oxygen, sulfur, and halogen donor. one point to be noted is that with Fe2 plus and Mn2 plus, NH3 act as weak field ligand. NH3 was basically a strong field ligand, but in with Fe2 plus and Mn2 plus, it acts as weak field ligand. So here is some important points that should be noted. So these are with copper 2 plus water, which is basically a weak field ligand, it acts as a strong field ligand with Cu2 plus. Similarly, F minus, which is also a weak field ligand, but with NiC4, it acts as strong field ligand. Similarly, H2O and C2O4 2 minus with cobalt 3 plus acts as strong field ligand. These are very important points and they to be remembered. So in this VBT chapter, what we have to find? So in this chapter, we will be given a complex and we have to find out the oxidation state of the central metal atom, the coordination number, hybridization of the central metal ion, geometry of the complex, number of unpaired electron present, spin only magnetic momentum, which is nothing but mu s, which is given by n into n plus 1, n plus 2 whole root over, which is nothing but n plus 1 whole square minus 1 whole root over bm, where n is the number of unpaired electron and bm is the Bohr magneton. And next we have to find out the nature of the given complex. So the nature on the basis of magnetic, so it is on the basis of magnetic nature, it is basically two type. It can be either paramagnetic or diamagnetic. On the basis of orbitals involved in hybridization, the complex compound may be two type, either inner orbital complex or outer orbital complex. Similarly, on the basis of spin of the complex, the given complex can be two type. It can be high spin complex or it can be low spin complex. All of this we will see in next page. So here is the hybridization and geometry of the given complex. So how to find out the hybridization and geometry? So basically this hybridization and geometry of the given complex depend upon the coordination number. So here it is the coordination number and its corresponding geometry and hybridization. If the coordination number is 2, then geometry is always linear and hybridization is SP. If coordination number is 3, then geometry is trigonal planar and hybridization is SP2. These two are fixed. For the coordination number 2 and 3, their hybridization and geometry is fixed. There is no other options. For the coordination number 4, there is two possible hybridization, DSP2 and SP3D. These are the only two possible valid hybridization for coordination number is equal to 4. No other options are there. If coordination number is 4, then hybridization is fixed. It can be either DSP2 or SP3. No other options. Here the D involved is dx square minus y square, which is also fixed. If the hybridization is dsp2, then the geometry will be square planar. If the hybridization is sp3, then geometry will be tetrahedral. Similarly, for coordination number 5, the shape is always trigonal pyramidal, and the possible hybridization is sp3d and dsp3. No other options are valid. Similarly, for the coordination number 6, the geometry is fixed, that is always octahedral, but there is two possibility of hybridization. These are d2 sp3 and another is sp3 d2. If the hybridization is d2 sp3, then the complex formed will be inner orbital. If the hybridization is sp3 d2, then the complex formed will be outer orbital complex. One thing we have to note that whenever S and Phi comes in the hybridization, they always from n orbital, that means the outermost orbital, but the d orbital can be n-1d or nd. If n-1d orbital is involved in hybridization, then it will be inner orbital complex. If nd orbital, that means the d orbital from outermost shell, then it will be outer orbital complex. So what are the steps that we have to follow? So here is the step. So first of all, we have to identify the central metal ion, and we have to find out the oxidation state and its coordination number, and coordination number is equal to the number of vacant orbitals required for hybridization. This point we should keep in our mind. And next we have to write the electronic configuration of central metal ion. In order to write the configuration of central metal ion, for this we have to first of all write the electronic configuration of corresponding neutral atom. Then we have to arrange them in increasing order of shell number. Then we have to remove required number of electrons from outermost shell to get the electronic configuration of central metal ion. And now we have to draw the orbital diagram, and then we have to fill the electrons by the help of Horn's rule of maximum multiplicity and Pauli's exclusion principle. And then we have to see the nature of ligand. If it is strong field, then we have to pair up. If it is weak field, then we do not have to pair. Then take that number of completely vacant orbital for hybridization, which equal to the coordination number. Whatever is the coordination number, we have to take that number of vacant orbitals for hybridization. So how to deal with exceptional cases? So if the coordination number is 4, then only and only two possible valid hybridization, these are sp3 and d2sp. No other options are possible. Similarly, for coordination number 6, only and only two possible valid hybridization are there. They are sp3d2 and d2sp3. No other options. If you are getting other than this, then you have to use two tricks, which is nothing but Fondo tricks, and we have to reach these hybridizations only. So what are tricks? If you are not getting valid hybridization, then in presence of SFL, we can shift one and only one electron, one and only one unpaired electron to higher orbitals, which is not required for hybridization, provided after the transfer of electron we get valid hybridization. That means if we are not getting valid hybridization, then in presence of SFL, we can shift one and only one electron to higher orbitals. If by doing so we get a valid hybridization. If electron is present in outermost s orbital, then always we have to backshift that electron, because s orbital of outermost shell should be always empty. First of all, we have to do maximum pairing. If we are not getting valid hybridization after maximum pairing, then we have to shift one electron forward shift. And by doing also, if you are not getting any valid hybridization, then you have to reduce the number of pairing gradually until we get a valid hybridization. So here is an example. We are given a complex which is K for Fe6, and we have to find out its oxidation number, coordination number, geometry, hybridization, nature, mu h, etc. So here step by step it is done here. First of all, identify central metal ion, which is Fe. Find out its oxidation state, which is F2 plus 2, and coordination number is 6. Once the coordination number is 6, its geometry is fixed, which is nothing but the octahedral. And you have to write down the electronic configuration of Fe2 plus. For this, you have to first write down the electronic configuration its corresponding neutral, that is Fe, then arrange. Then you have to remove 2 electrons from last shell, that means from 4s. Then you will get the electronic configuration of Fe2 plus, which is like this. And this is the trick which is used for writing the electronic configuration. And now we have to draw the orbital diagram, which is like this, and we have to fill the electrons. And the ligand is Cn minus, which is strong field, so pairing will take place. After pairing, it is something like this. And since the coordination number is 6, orbital required for hybridization will be 6. You have to take these 6 vacant orbital, which is 2d, then it is from s, and 3 from p. So the hybridization will be d2sp3. So this d orbital is from inner orbital, so the complex form will be inner orbital complex. And here the number of unpaired electron is 0, so mu will be 0. So there is no unpaired electron, so the nature of complex will be diamagnetic. Geometry will be octahedral, hybridization will be d2sp3, that means it is inner orbital complex. Since the number of unpaired electron has reduced, so the complex form will be low spin complex. So that's it. Thank you.